Hi everyone, I'm Sebastian Brandt and this is joint work with Alkida, Balliu and Dennis Olivetti from University of Freiburg and Jukka Suomela from Aalto University. The question we want to ask in today's talk is how much can we profit from having randomness available in the local model? Which is a question that has been termed perhaps the most fundamental open problem in the local model by Barenboim and Elkin in their book on graph coloring. Now, for such a question, of course, it is highly relevant how exactly our model of computation is specified and what is the class of problems we're looking at. So let's take a look at those. The model of computation will be just the usual local model where we want to solve some graph problem in a distributed fashion. Each node of the input graph is a computational entity that tries to solve the problem. Each edge is a communication link over which the entities can communicate. The whole computation proceeds in synchronous rounds, where in each round, each node is allowed to send an arbitrarily large message to each neighbor. And when the messages arrive, each node is also allowed to perform some arbitrarily complex local computation. In the end of such a computation, each node has to output its local part of a global solution to the problem. Our measure of complexity, so the runtime of such a distributed algorithm, is just the number of synchronous rounds until the last node terminates. The class of problems we are interested in are so-called LCL problems, which are problems that, first of all, are locally checkable. A locally checkable problem is a problem that can be described via local constraints. For instance, vertex coloring is a locally checkable problem because we can describe it by just requiring for each edge that the two endpoints have a different color. And most problems that we are interested in the local model are actually locally checkable. So all kinds of coloring problems, maximal matching, maximal independent set, Lover's log lemma, all these problems are locally checkable. We also allow inputs in such a locally checkable problem. For instance, list coloring is such a problem where on top of the usual coloring constraint, we also require that each node picks its own color from its own list. LCL problems are locally checkable problems that are defined on bounded degree graphs and that require that we only use a constant number of labels to describe the problem. LCL problems are probably the best studied major class of problems in the local model. In particular, we know a lot about the possible complexities LCL problems can take on. So to put this into a picture, here we have the deterministic complexity on the x-axis and the randomized complexity on the y-axis. And now we can put some dots into this picture that correspond to problems with the respective deterministic and randomized complexity. For instance, we know that there are problems that have deterministic and randomized complexity both theta of n, or both theta of log n, or essentially anything in between. But we also know problems that have a different randomized and deterministic complexity. For instance, we have problems that have randomized complexity log n and deterministic complexity log n. One such problem is the sinkless orientation problem, where the task is to orient all edges of the input graph such that no node is a sink. So each node has at least one outgoing edge. Except if your degree is too small, if your degree is 2 or smaller, then you are exempt from having to have an outgoing edge. Now, interestingly, we do not only know points for which problems with the respective complexities exist, but we also know large gaps. So we know that for all points in these colored areas, there is no problem with the respective randomized and deterministic complexities. So the only regions where we don't know yet whether there are any problems that live in these regions are this white area up here and this white region here. But for the lower region, it is conjectured by Chang and Petty that actually no LCL problem lives in this region. One of the results that led to this gap results, which will be of particular interest for us today because it talks about the randomized, the relation between randomized and deterministic complexities, is a result by Chang, Kopelowitz, and Petty from 2016. It states that the randomized complexity of any LCL problem is at least the deterministic complexity of the same LCL problem on instances of size root log n. So what this means for us is that we cannot profit more than exponentially from randomness. We actually know problems where we profit exponentially from randomness, for instance, synchronous orientation. But interestingly, all problems for which we know both deterministic and randomized complexity asymptotically that do not fall into this blob here have asymptotically the same randomized and deterministic complexity. So one big open question here is, are there problems where we benefit non-trivially but sub-exponentially from randomness? For instance, are there problems where we profit polynomially from randomness? And it would be great if the answer was no, because then one just would have to show that one can profit a tiny little bit from randomness to obtain that one immediately profits exponentially from randomness. Unfortunately, we show that there are problems that profit polynomially from randomness. So there are problems that live in this white area here. And in particular, we show that for any positive integer I, there are LCL problems with complexities log to the I+1 of n deterministically, and randomized complexity that is the same, just one log n factor is replaced by a log n factor. On a very high level, we obtain these problems in the following way. We start with some problem pi0 that has the mentioned exponential gap between deterministic and randomized complexity. So for instance, we could pick synchronous orientation for pi0. And then we somehow pad this problem, and we will see what that means, to get a new problem pi1, where we have an additional log n factor in both the deterministic and the randomized complexity. And then we can iteratively apply this procedure to get a new problem pi2 with even one more log n factor in both complexities, and so on, to achieve exactly the mentioned complexities. Now, when designing LCL problems that are supposed to have some specific complexity, what is useful is to first think about what should be the worst case instances for the problem we are about to design. So what we want is we want to choose some family of input instances for which we can show that the problem we are about to define is already as hard on these instances as in the general case. And of course, such a family somehow has to come with some intuition, some idea of how we want to define the problem on this instance. This will not necessarily fully specify the problem, maybe not even on these instances, but it will give us an intuition how we want to achieve the desired complexities. And then in the last step, what we want to do is to refine the problem definition, so to get a fully specified LCL problem, for which we can both show that on our family of input instances, we get the desired complexity, and also that on all the other instances, all the other possible instances, we do not get a higher complexity. Now, in our setting, we are not given a precise complexity that we have to achieve with our new LCL problem, but rather we are given some LCL problem pi0 with some randomized and deterministic complexity, and we want to find a new LCL problem pi1 where we have both deterministic and randomized complexity increased by a log n factor. So how do we get such a worst case family of input instances for this task? The idea that we want to follow is the following. Let's start with a graph with roughly root n nodes. And let's now replace each node with some gadget, so some subgraph that also has roughly root n nodes. So in total, we get n nodes in the graph. And that also has the property that any two edges leaving the gadget, so any two edges that were incident to the same node in the original graph, now have a distance of theta of log n. We do not allow every graph with these properties, every subgraph with these properties to replace a node, but we specify explicitly some family of such gadgets And then our worst case instance family G will be exactly all graphs that we can obtain by taking a roughly root n node graph and replacing each node by one gadget from this family F, where we are also allowed to replace different nodes with different gadgets. Our rough idea how we want to define pi1 on this graph class is it should be equivalent to solving pi0 on the contracted graph that we obtain by replacing these gadgets by their original nodes. And if we can define in a locally checkable way such a problem pi1, then what we would get is that the complexity of pi1 is the complexity of solving our original problem pi0 on these root n node graphs times a log n overhead, because we need essentially log n rounds each time our communication has to cross a node. And since the complexities of all problems of interest for pi0 are polylogarithmic, we can also replace this root n simply by an n, and then we get the statement that the complexity of pi1 is exactly a log n factor higher than the complexity of pi0, asymptotically speaking. So this is just on our instances in the graph class G. And what we have to do now is to show two things. The first one being that we can define a problem pi1 that is equivalent to pi0 on the contracted graph in a locally checkable manner. And the second is that all the other instances that are not in G are not harder to solve. So let's start with the first. For our gadget family F, we only take gadgets that come with a marking of its edges. Okay, so each node in one of these n node graphs knows whether an incident edge is a gadget edge or one of the original edges. And if you don't like having inputs, then one can also encode this in the topology of a graph. So it's possible to do this without input labels, but it is much more convenient to do it with them. Now, we define pi1 on our graphs in G in the following way. We say each node in a gadget has to give a correct output for the problem pi0 on the contracted graph, so for the node that corresponds to this gadget. For instance, if the problem pi0 is singles orientation, each node in the gadget has to give a correct output for correct local output for the singles orientation problem for the node corresponding to this gadget. So it has to orient the incident edges. And we realize this in a locally checkable fashion by requiring that any two neighboring nodes in the gadget output the exact same orientation for the incident edges of the contracted node. And then we also require that for each edge that is not marked as a gadget edge, so each edge of the original graph, the two endpoints in their encoding specify the same orientation for the connecting edge. And in this way, we have a description of a problem pi1 via local constraints that exactly specifies a problem that is equivalent to solving pi0 on the contracted graph. So let's go to the second step that we have to show. And that is that for all other instances, we can be as fast as on our worst case family G. Now for this, it is useful to extend our definition of gadgets also to hold on such graphs. So we define now a gadget as a maximal induced subgraph that is connected via gadget edges, which are marked in red here. So we want to be able to walk from each node in the gadget to each other node, to any other node, via these red edges without leaving the gadget. Which does not say that there is no edge that is not marked as a gadget edge in such a gadget. That is just something that cannot occur in any graph in G, but now on our general bounded degree graphs, this can happen. Now we distinguish two kinds of gadgets, valid gadgets and invalid gadgets. An invalid gadget is defined as containing at least one node that by just looking at its constant hop neighborhood, so something that we can describe in a local constraint, can determine that it is not in a graph in G. Okay, so this node here, it has two neighbors connected via gadget edges that themselves are connected by an edge that is not a gadget edge. And this is something that cannot occur in any graph in G. So this node, but just looking at its constant hop neighborhood, knows it is a node of this kind. And also this node here, since it has two incident edges that are both not marked as a gadget edge, knows it is not, it is one of these edges. And now we extend our definition of pi1 in the following way. We allow that all the nodes that satisfy this local criterion are allowed to output error, which is just one other output label in our problem pi1. Now, not all nodes satisfy this local criterion, even if they are contained in invalid gadgets. So we add another new output to our problem definition that is just an error pointer, which means the node outputs a pointer to a neighboring node. And the local constraints on error pointers is that, essentially speaking, if you point to a neighbor with an arrow pointer, this neighbor also has to output an arrow pointer, or it has to output error. So for instance, this would be, locally speaking, a correct output because each node that outputs an arrow pointer points to a neighbor that also outputs an arrow pointer or outputs error. Now there are some more constraints on arrow pointers. The essential thing for us is that arrow pointers are defined in a way, and arrows also, that they cannot be used in any of our graphs G. There's just no globally correct solution that uses those. But in any invalid gadgets, they provide us with a way to find a correct output for each node in theta of log n rounds, just by doing the following. Any node that is allowed to output error, outputs error, and any other node, well, tries to output an arrow pointer on its shortest path to an error. Now, since any node, one can show that any node has a node that is allowed to output an error in its theta of log n hop distance, we know that we can solve invalid gadgets in theta of log n rounds, which also tells us that in worst case instances, such invalid gadgets cannot appear. So we can now restrict attention to graphs that only consist of valid gadgets. So of gadgets where every point has a constant hop, every node has a constant hop neighborhood that occurs in some graph in G. But the graph consisting of these invalid gadgets itself does not have necessarily have to be a graph in G. So to solve this last remaining class of graphs, to show that our problem pi1 is not harder on these graphs than on the graphs in G, we should look at the structure of the gadgets that we actually use in G. So as mentioned before, these gadgets consist of root n nodes, and structurally they have one central node, and from this central node we have a constant number of sub-gadgets hanging, which are all identical and all consist of one tree, one perfect binary tree, where we have nodes on the same level connected via one path. The last node of such a sub-gadget, so the rightmost leaf, if you will, has one outgoing edge to another gadget. So in particular, if the original node is of degree D, we have to replace it by a gadget that contains exactly D sub-gadgets. All right, so the number of nodes tells us that the depth of each sub-gadget is logarithmic in n, which also tells us that the distance between any two edges leaving the gadget is also logarithmic in n. For valid gadgets, we can infer from the particular structure of our gadgets that we use in G, that they must have the same structure. Except that, well, the number of nodes in such a gadget might be different from root n. It could be anything from constant to n. And also, the depth of the subgadgets might be different for different subgadgets. So we could have some subgadgets of, say, constant depth, and one subgadget where we have almost n nodes in the subgadget. But the nice thing is that even if we put n nodes into a subgadget, the depth of the subgadget will still be logarithmic in n, at most. So any two edges that leave such a gadget still have a distance of at most logarithmic in n. And well, now we can use the the original definition of pi1, which is that we have to solve pi0 on the contracted graph in the same fashion as we solve the graphs on G. In the graphs that just consist of valid gadgets, we just solve the graph, the graph problem by solving pi0 on the contracted graphs, and we incur the same logarithmic overhead each time we have to pass a node. So this concludes the proof that also on all other instances, on all instances that are not in G, we do not get a higher complexity than in G. And as we have already seen in G, we get the desired complexities. To summarize, we have shown that there are problems that profit only polynomially from randomness, but non-trivially, that live in this wide area up here. And more specifically, we give these exact asymptotic complexities for these problems. Now, let me conclude with some open problems. So all the LCL problems that we designed have a ratio between their deterministic and randomized complexity of log n divided by log n. Now, one question is, can we design LCL problems with a higher ratio? Which is a question that is closely related to a de-randomization result by Ghaffari, Harris, and Kuhn that says that the deterministic complexity of an LCL problem is at most the randomized complexity of the LCL problem times a factor that is the sum of log squared n in the time it takes to compute an object called log n network decomposition deterministically. Or put it a bit differently, this ratio is at most the sum of log squared n and the time it takes to compute the network decomposition. Now, if we could tweak our design somewhat to obtain LCL problems with complexity little omega of log squared n, then this would immediately give the same lower bound for the problem of computing such a network decomposition, which is a huge open problem in the local model. One other open question concerns, well, decidability in the following sense. We have seen that there are problems that profit exponentially, problems that profit polynomially, and problems that do not profit at all from randomness. So it would be nice to have a way to decide for any given LCL problem into which of those categories it falls. And another question that I find very interesting concerns these desirable gap results. So we saw that for LCL problems, we do not get a gap. We have intermediate problems between exponential profit and trivial profit from randomness. So maybe we are looking at the slightly wrong class of problems for this purpose. Maybe we can tweak our class of considered problems a tiny bit, such that these intermediate problems vanish. So we actually get a desired gap result and can use it for instance for speeding up algorithms. So this would be very interesting. And that is all I have. Thanks for watching. I hope you enjoyed it. And if you have any questions, let me know.